In this video, this is Chapter 3, we're going to be discussing ways to summarize numerical data. Not necessarily in a graph or a table like we did in Chapter 2, but more along the lines of how we can summarize it numerically into a statistic. Mean, median, and mode are three ways we can measure what's called central tendency. In other words, it's a way of describing the data by telling what the middle of the data looks like, or the center of the data. So in describing the mean, median, and mode, we come up with these three formulas for each. The mean, another word for mean, is a lot of people know it by the word average. Mean is also called the average. We know how to find the average of a set of data. We add them all up, or we take the sum of all of the individual data values, and then we divide it by how many were in the data set. Notice at this time we're going to be starting to use different notation for some of these items. This Greek letter is called mu. It looks like a U, but it's actually a cursive M, which stands for the Greek letter mu. Mu is what's called the population mean. So if we were taking the average or the mean of the whole population, we would use the letter mu. On the other hand, if we were taking the average of just a smaller sample of the population, then we would do the same formula. We would take the sum of all of the data points in just the sample, divide by the number in the sample, and we come up with what's called X bar. X bar is what we use as the statistic that tells us the average or mean of a sample. So even though these two values may or may not be different, they both mean mean, but we will describe them with two different variables. Also notice that capital N is used for the number in the population, but lowercase n is used for the number that's in your sample. So if we were looking at a Venn diagram, for example, this would be my population. A smaller sample inside that population would look like this. So we would have n number of items in the sample, but we would have n number of items total in the population. When talking about median, we know median as being the middle of the graph. So basically what you need to do is arrange the data in ascending order or descending, it doesn't really matter, but they have to be in order, and then you divide the data set in half, and the middle value would be the median. Basically what this does is divides the bottom 50% from the top 50%. Mode is what's called the most frequent. What you're going to do to find the mode is tally each of the individual items and find the item that occurs the most frequent, and that would be your mode. So we're going to do an example of this now. Let's say we have the following 5 test scores: 83, 65, 91, 87, 79, and 84, and let's find the mean, median, and mode. The mean is found by adding all the values together and dividing by the number of items that there are. So we need to add 83 plus 65 plus 91 plus 87 plus 79 plus 84, and then we're going to divide that by how many items there are. There are 1, 2, 3, 4, 5, 6 items. And when we put this in our calculator, we're going to get an average score of 81.5. Now, if this was just a sample of 5, I'm assuming 5 is just a sample of the whole class. Let's say the whole class had 30 students, and 5 is just a sample of that. We would call this X bar. Now to find the median, we have to put them in order and find the middle value. So the first thing we're going to have to do to find the median is put these values in order. So we're going to start with the lowest, 65. Then we have 79, and then 83, 84, and then we have 87 and 91. Since there are 6 values, there's not going to be a middle value. There are 3 numbers on this side, and there are 3 numbers on this side, so the middle value is actually going to be whatever is in between these 2 values. So there is no middle. So in order to determine what the median is, to find this fictitious middle point right here, we have to take the average of these 2 values. So the median is going to be found by adding 83 and 84 and dividing by 2, which gives me 83.5. Now the mode is found by determining which value happens the most often. And since each of these values only happens one time, there is actually no mode for this example. Now, however, what if we add what's called an extreme value and then recalculate? For example, let's say I add the number 10 onto the very end here. Let me rewrite all of these scores: 65, 79, 83, 84, 87, and 91. So we're going to use this value as the extreme value, meaning it's much smaller or much bigger than the other values. So this extreme value, someone scored a 10 on their exam, is going to change the mean, median, and possibly mode. So let's see what happens. Let's recalculate the mean. To recalculate the mean, again, what I do is I add all 7 values and divide by 7. When I do that, I get 71.3. This is a good time to pause your video and make sure you get the same value. The median is found by taking the middle of this data set. Well, this data set has 3 values on this side, 3 values on this side, so the median will be 83. Again, there is no mode. No term happens more than once. So the question says, which is more resistant, the median or the mean? Resistant means resistant to change. In other words, which of these 2 values did not change that much? The mean changed from 81.5 down to 71.3. So it went down a whole 10 numbers or integers based on adding this extra value. The median changed from 83.5 down to 83. Since it did not change that much, it would be called resistant. So the median is resistant. Since the median is resistant, we say that the mean is not. Usually when we add an extreme value, something that's really small or really big, it's going to take that mean and it's going to draw it down towards that small value. Now, what if we took the original 6 test scores and we added an additional score of 83? What would the mode be? So here's my original scores right up here. And we added an additional 83, so right in there. So we have 65, 79, 83. Now we have an additional 83, 84, 87, and 91. It asks what would my mode be? Well, now my mode would be 83 because 83 occurs twice, and it occurs more often than any other value. What if we took the original 6 test scores and we added an additional 83 and 87? So my data set now looks like 65, 79, 83 with my additional 83, 84, 87 with my additional 87, and 91. The mode would actually be both numbers. It would be both 83 and 87. and it would be both numbers because each of those data sets occurs more often than any other. Now, however, if there was another 87 here, then the mode would only be 87 because it occurs 3 times, which is more often than 83 and certainly more often than any of these other numbers. So it'll be the data number that occurs the most often. If they all occur the same amount, then there is no mode. So moving on to the next page, now we're going to talk about the distribution of data and how they are skewed. So we briefly talked about this in Chapter 2, and skewness occurs when certain things happen with the mean and the median. So there are always going to be extreme values in the tail which tend to pull the mean in that direction. So if the distribution is skewed left, which what this graph is right here, this is a skewed left graph. In a skewed left graph, the mean is substantially smaller than the median. So you could see that here. This mean is substantially smaller than the median because you have that extreme value or possibly outlier way over here like we did on the previous page, and it's going to pull that mean in the direction of the tail. The median hardly changes. The median usually is at the peak where the mode is, but because of that extreme value, it pulled the median a little bit, but not too much because it's resistant, but it really pulled the mean in the direction of that outlier or that extreme value. Now on the other side, if it is skewed right, it looks like this graph over here. In a skewed right graph, the mean is going to be in the tail off to the right. You're going to have an extreme value that's really high, and it's going to pull the median away from the mode slightly, but it's going to pull the median, and the mean, farther into the tail because of that extreme value. The mean is not as resistant as the median. Now a graph that's symmetric, however, the mean and the median are roughly equal to each other in the middle. The mean, median, and mode all occur in the middle. So how would we expect the previous example to be distributed? So when we looked at the previous example, in this data set right here, how would we expect this to be distributed? Well, there is no extreme value, so I would expect this to be fairly symmetrical. The mean and the median are roughly the same number, so this would be roughly symmetrical. So if I were looking at a graph of this, it would probably be something symmetrical like that. However, once we add this additional value, this extremely low value, the mean then becomes much lower than the median, and this extreme value is going to skew my data, which used to be here in the middle, is now going to skew it to the left, because that extreme small value of 10 is going to pull the mean into the left. So the mean will be over here, where the median will be unchanged or slightly changed. At this point, we became familiar with a couple of these variables. Well, we said that capital N stands for the number of observations in the population, where little n is the number of observations in the sample. That should say sample. X1, X2, and so on, X3 up through X whatever, are the actual observations, so they'll all have a different designation. This will be the first data point, second data point, and so on. Where X bar is the sample mean and mu is the population mean. Sigma indicates that we are supposed to take a sum, so you'll find this sum in the numerator of the mean formula. So here's an example I'd like you to think about. So after I read the problem, I'd like you to pause the video and think about it before you press play. Suppose you have to choose which exam to take, Test A, Test B, or Test C. So you're going to find the mean and the median of each of these data sets. And I want you to decide which of these you'd rather take and why. Okay, so hopefully you paused the video and you found the median and the mode of all three. Let's do that here. The mean and the median of all three. The mean for all of these was 70. So at first glance, it doesn't look like any of these tests are different than the other, but clearly by looking at the data, you can tell that these are different data sets, but they all do give the exact same mean. So let's look at the median. Maybe that will help us in determining which of the tests I'd rather take. If I look at the median of each of this data set, the middle value is 70. The middle value here is 70, and the middle value here is 70. So unfortunately, by looking at the mean and the median, it doesn't really give me an idea of which test I'd rather take by using only these two sets of statistics. I wouldn't be able to really make that decision. However, if I look at this data a little bit more carefully, I can look at, okay, this last one is very low risk. I'm pretty much guaranteed to get a C on the test. So that might make me feel good because I'm guaranteed to pass. However, if I really want an A, then I might want to consider taking either test A or test B because I have more chance of getting an A, but I also have a higher chance of failing. So these are more risky, but also possibly more rewarding, where this one's a little more lower risk. So they're clearly different ideas to this approach, but only looking at the mean and the median isn't going to be enough to determine what the differences between these data sets are. We need actually one more type of statistic that can measure something other than just the middle of this data. What else can I use that will also take into consideration the range of the data, in other words, how widespread this data is? And that's what the next topic is on the next page. In the next section, we're talking about measures of dispersion. Dispersion is another word for variability or range. Okay. So the dispersion is the degree in how widespread the data is. If two or more data sets have the same mean, it doesn't necessarily mean that they have the same patterns, as we saw in the previous example. One set of data could be very spread out where the other could be all grouped closely together. Again, just like the previous example. The simplest measure of dispersion is called the range. This is a very simple technique to use. The range is simply by definition the biggest minus the smallest. So let's go back to the previous example and find the range of all tests A, B, and C. So if I go back to the previous page again and I look at these examples and I want to find the range is the largest minus the smallest. So here is going to be 90 minus 50, which is 40. So the first data set from test A has a range of 40, or 40 wide from the smallest to the biggest. Test B also has a range of 40 because it's also 90 minus 50. The last test C has a range of 70 minus 70, or 0. In other words, all the points are the same. None of them are any different or spread apart. But what the range does is only takes into consideration the smallest and the biggest and not any other data points that might be in between as well. So we're still missing a little bit of that dispersion aspect that takes into consideration these other values that are inside, not necessarily the middle, but not necessarily the largest and the smallest. So the range, just to rewrite those in my notes, was 40, 40, and 0. So you should start to notice that the range is affected by extreme values in the data set. So the range is not resistant. Also, the range is computed using only two values. It does not take into consideration all of the middle information. So what we use is this last statistic that we're going to talk about, which is called standard deviation. Standard deviation uses all the data values in all of its computation, the middle, the extreme values, and also all the values in between there. Standard deviation is based on the distance, or the deviation, that each data point is from the mean. So here's some formulas for you. This is sigma, another Greek letter for you. Sigma looks like a circle with a hat, and it is the population standard deviation. We usually actually don't have this information because generally we don't have all of the data from the whole population, since it's really hard to gather all of that. So we're probably just going to focus on sample standard deviation for the rest of this book. Sample standard deviation is designated by the letter S. So sample standard deviation is lowercase. So let's look at the definition of the sample standard deviation. This sample standard deviation by hand is quite a complex formula. There are simpler methods, which I will show you in a moment, but to do it by hand, we have to use this formula. There is this formula, and then there's also an equivalent computational formula that we can use down here, which is a little bit easier to use. They both result in the same answer, but this one might be a little easier to use from a computational standpoint. Let's just go through each of these values so you know what they are. Again, S stands for sample standard deviation. X1, X2, all the way up through Xn are the individual data values, or whatever's in your data set. X bar is the sample mean, and little n stands for the number in your sample. Why we subtracted from 1, we will get to in future sections. They talk a little bit about it right here, but why we subtract from 1, we'll get to in future sections. Also, we could do the computational form, which is down here. It says we take the sum of all of the x values. So these are all of your data points, and if you square each of your data points, you take the sum of all of those squares, and then we subtract the sum of all of the data points collectively, then squared, divided by the sample size, divided by n minus 1, all under the square root. So either one of those we can use, which we're going to do now. So we're going to go back to that example that I just described with the test scores. And I briefly go over why we subtract from 1 here. So we call the n minus 1 that's in the denominator of the standard deviation formula, we actually call that the degrees of freedom. N minus 1 observations has freedom to be whatever they wish, but the nth value has no freedom. It must be whatever value forces the sum of the deviations to go about the mean and have it equal to 0. So give you an easy example of that. Let's say there are 20 people that walk into the classroom. So n is 20. There are 20 chairs in the classroom, right? So the first person that walks in can sit in any chair they want. They have the freedom to decide wherever they'd like to sit. The second person that walks in has the freedom to decide wherever they'd like to sit. So for example, the 20th person that walks in can go to anywhere they want. The 19th person that walks in can go to wherever they like, and so on and so forth. But when we get down to the very last person, when they walk in, they don't have any freedom. There's only one chair left. So they are forced to sit in that last chair because that's the only way to make it work. That's what this is saying, is you always have one less degree freedom than you have the number in your sample. So all of the others have the freedom to be whatever they want. All x's or variables can change. But that last value does not have freedom. It is forced to be a particular value in order to make an equation come true. So we only have one less degree of freedom. So let's go back to the example. We're given that data set over here that we had on the previous page, and now we're going to calculate the standard deviation of each of those three examples. Okay, so doing these by hand, we have test A. Test A had the following 5 values. So the computational formula, if we remember back from the previous page, let me write it here. The computational formula was given by standard deviation, which was equal to the sum of the individual x's squared minus the sum of the individual x's quantity squared divided by the number in your sample, all over n minus 1, and we put that all under the square root. So we're going to do that calculation here for all three tests. The first thing we need to do is fill in the table. The things that we need from the table is we need to find each of the individual x's and the sum of all of those. So we need all of these individual x's. We need to add all of those values together. So if I put all of those values into my calculator and add all 5 values up, you're going to get a total of 350. And again, at any point during this video, I would suggest you pause it and check these values with what you also get. In the next column, I'm going to square each of the individual x's and then sum up that whole column. So I'm going to square 50, which gives me 2,500. I'm going to square 60, which gives me 3,600, and so on. Once I square each of the individual values, now I sum that whole column. So when I add this whole column up, I get 25,500. So what I have just found is this value is the sum of the x squares, so that's this value right here. I've also found the sum of the individual x's, which is going to be this value right in here. So I'm going to plug those values in, and I'll calculate this using my calculator. So right here is the sum of the x squares, which is going to be the 25,500. Then we're going to subtract the sum of the x's, which is this number, squared. That's divided by n. So we divide by the number of items in my range, which is 5. Then we divide all of that by n minus 1, which is 5 minus 1. So we're going to put this all in my calculator and calculate. So I'm going to do that here. All right. So over here in my calculator, let's do square root of, I'm going to put the numerator in parentheses, so 25,500 minus 350 squared divided by 5, and then I'm going to divide that by 5 minus 1. And I get approximately 15.8 is my standard deviation. And what that means is that each of these values, each of these individual values, are approximately 15.8 in distance or away from the mean. So if this is my mean, 70, all of the other values are an average of 15.8 away from the mean. So it's taking the average of all of the deviations away from the middle of the graph. So let's go ahead and recalculate it for the next two examples. I'm going to let you pause it at this point and go ahead and do the second and the third test, and then when you come back, you can check your answers with mine. Okay, hopefully you paused the video and you calculated your test B and test C, and here's the calculations that I have done also. You can see that I calculated all of the first column, which those are the same all the way down. Let's see, the second column though is different. So because when we square each of the values, we're getting a different sum each time. Over here, when we do our standard deviation, you can see that even though the second number is the same, the first number is changing. So when we put this into our calculators, you can see we started with a standard deviation of 15.8, then it went down to 14.1, and then it went down to 0. So the standard deviation has decreased by the time we get to the bottom. This one has a standard deviation of 0 because each of these values are a distance of 0 from the mean. Remember, the mean and the median was 70. So how far are each of these other values from the mean? Well, they're 0 away, so the standard deviation is 0 because all of them are the same value, which is the mean. You can see that this one has a smaller standard deviation because we have more values that are right at the mean and only 2 values that are away from the mean. So it's going to have a smaller deviation because only 2 values are away from the mean, where this one has 1, 2, 3, 4 values that are away from the mean. So in the question underneath, when it asks you what observation can you make with the standard deviation using the above data, we could say that the smaller the deviation is, the smaller the dispersion is from the mean. So if a data set has a lot of observations that are far from the mean, the sum of the squared deviations will be large, and therefore the standard deviation will be large. All right, so let's do another example, and then I'll also show you how to do all of this in StatCrunch. So let's say that I teach 2 Math 136 classes, and they have the same average math SAT score. Class A has a standard deviation of 25 points. Class B has a standard deviation of 75 points. Which class would be easier for me to teach? So at this point, I'd like you to pause the video and think about this question. Once you're back, we can discuss. So Class A has a smaller standard deviation. So what does that mean? So Class A, since it has a smaller standard deviation, it means that more students will have alike intelligence levels, right? So they're all very close to having the same test score, so they're all very close with knowledge of content. Class B, however, has a standard deviation of 75. So which means even though they might have the same average IQ or test score, they have larger deviation, which means they're going to have more students that are possibly not up to the average, and also on the other side, more students that are higher or above the average. So in this regard, I think the lesser the dispersion means similar intellects. In the classroom. And I think that this would be the easier class to teach since they all have a similar knowledge base. Now, there is a third measure of dispersion. This is the third and the final measure. It is called variance. Variance, by definition, it's a variable which is just basically the square of the standard deviation. So if you know what the standard deviation is, all you have to do is square it, and then you have the variance, okay? So by definition, variance is equal to your standard deviation squared. So it's really not a new statistic. It's just basically taking the standard deviation and squaring it, okay? If we wanted to talk about population variance, then we would use sigma squared because S is for the sample and sigma is for the population. The variance is easy to calculate. Again, all you need to do is square that value. So let's go back to tests A, B, and C, and let's find the variance for test A, test B, and test C. From the previous page, the variance of A is going to be the sample standard deviation squared, and the standard deviation was 15.8 rounded. And when we square that, we're going to get 249.6 is the variance. For B, the sample standard deviation was approximately 14.1. And when I square that, I will get a variance of 198.8. And lastly, the variance of C will be the standard deviation squared, which is 0, which clearly is 0. If you notice from the previous page, the standard deviation actually had these square root symbols. So if you just take off the square root symbol, everything underneath here really is the variance. This was the variance. Once we take the square root, that's when we get the sample standard deviation. So if you want to find the exact variance, you would just calculate everything that's underneath the square root and just not take the square root of that number. All right, so lastly on this page, we're going to now check all of these values in StatCrunch. So let me switch you over to StatCrunch. So once you are in StatCrunch, what you're going to do is you're going to click on the StatCrunch button, which is in your MyMathLab over here on the left-hand side of your MyMathLab. So once you're in StatCrunch right here, when you click on that, then you're going to click on StatCrunch website. So once you click on the StatCrunch website, it's going to open up in a new tab, where we can enter our data. So what it asks us to do in the lecture notes is we're going to enter all of the data from the previous page into a column. So let's go ahead and enter all of the data from tests A, B, and C. So let me go ahead and rename each of these variables as test A, B, and test C. Test A has the data of 50, 60, 70, 80, and 90. Test B has data 50, 70, 70, 70, and 90. And test C has data 70 all the way down. Okay, once we have all of the data entered in, what we can do now is we can find all of these sample statistics that we've just found in the previous couple pages. So what we're going to do is we're going to go up to Stat, and that's where we find all of the statistics that we need. And we're going to go to Summary. We want to summarize all of the data in the columns that we've created. So let's now go to by column, because we put all of our data in columns, not rows. So once we click on columns, it's going to ask us to select the statistics we wish to find. So first we want to find all the statistics for each of these. So let's go ahead and click on each of them. So we're going to do A, B, and C. So in order to select them all, you need to click one and then use the control button to click the other so you can select them all. And you notice each time I select them, they'll all show up over here. I want to show the statistics for each of these samples. If you only select one, it will only show the statistics for just that one column. I want to put these in order. Let's try again. There we go. Okay. So then down here, we're going to select the statistics that we want to show. So let's select N. Let's find the mean. Let's add variance. Let's add standard deviation. Let's add median, range. And that's about it. That's all we want to do. Okay. So when you're doing standard deviation, you want to make sure you're selecting standard deviations for samples. If this was a population, you would select unadjusted standard deviation, which means they don't divide by the n-1 and they leave it just divided by everybody. So we leave the unadjusted variance and standard deviation for populations. So we're going to use, for the most of this book, we're going to be using the regular variance and standard deviation, which is for samples. Okay, so once we have all the ones we selected that we want to show in the report, we're just going to go ahead and compute. So it's going to come up in a table, so you can see that right here. Okay, So in this table, it shows all the 3 different tests. There were 5 sets of data in each of those tests. Remember, we found the median. It was 70 for each, and the median was 70 for each, but we calculated those by hand. We then found the range. The range we found was 40 for the first 2 and 0 for the last by doing biggest minus smallest. And then lastly, we went through and we found the standard deviation and the variance. So the standard deviation should match. It was 15.8, which we found on the previous page, and the standard deviation for test B was 14.1. Now, when we squared those numbers by hand, we found something slightly different than these. We found like 249.6 and 198.8. That's because we rounded these numbers. If we would have squared this whole value, all of this, if we would have squared everything, we would have gotten 250 or 200. So this is a good way to do the same thing that we did by hand, but this is a much faster technique by doing it in StatCrunch.